Oh, can you hear me?
Yes, Bob. We can hear
Okay,
you. We can see you.
all right. I
Hi.
just wanted to test that things were working. Vikesh was assisting me yesterday on trying on the share screening, and hopefully that will work, but there may be problems with it.
Yeah, actually, you can share the screen right now so that we know that that's working and then your first slide can remain on.
Uh, I didn't quite hear you. Try again.
You can share the screen right now, even before I start the session, so
Okay,
that your first slide is there, and then we will know
let's
that
see.
all is working.
Let's give it a try. Uh, I press this, which is the right thing, and I press this.
Yes, we see your screen and it's perfect.
Uh, but I can't see it, so that's.
Oh, okay.
But let me remove it again, and let's see. I think I can unshare it and play another trick here. Uh, Presentation. This is yeah right now. Now I can see something, and
We can't see now.
all right. Let me try and put it up and see if this will work. Can you see
Yes,
something?
we can see your screen now. It's fine.
Okay, and I can see it. So
Good.
I think
Just
everything.
change one slide and come back so that we
All
know
right.
everything is working.
Yeah. Let's see. Uh, all right. That changes the slide, and that changes. Okay, I can do it either with the mouse or the keyboard. The trouble is, they work in the opposite direction. But
Yeah, so now we are on the first slide, so everything is fine. We'll
okay,
just wait 2 more minutes, then we'll start the
and
session.
then start. Okay. Hmm.
People are slowly joining. So must be early morning for you.
Not very early. It's 9 in the morning. So,
Mhm, okay.
Hello, Bob. Lovely to see you.
hello.
It's Kavita here. Can you see me?
Yes.
Okay, so lovely to see you. And too bad this time we couldn't have you over physically. It has to be done online. But hopefully, 2021 we'll get you over here.
Uh, I do not travel very well these days, I'm afraid. So
Okay,
this is probably the best I can do, but I will try and do it. So,
okay.
All right, so it's time to start this session. I welcome you all to this session of QFTA 20. There are two speakers in the session. First speaker is Professor Robert Griffiths. It's a matter of honor to chair a session in which he is a speaker. Professor Griffiths' connection with India goes back to the fact that he was born in India. He did his schooling in India. After that, of course, he moved to Princeton, did his PhD, and did various stints at various places. He has been at Carnegie Mellon University for more than 50 years, and he has recently retired from there, and now he's an emeritus professor. Well, I have a special connection because I spent 2 years with him at CMU. And within the physics community, there are two extremely important things: the Griffiths phases in condensed matter physics and Griffiths consistent histories interpretation in foundations of quantum mechanics, which he's very well known for. And he's also very fortunate that both these important works are associated directly with his name. I was just looking at the titles of papers which have Griffiths phases in their title, and you can see them in over the years, a large number. And of course, the consistent histories. Today, he's going to talk about what quantum measurements measure. And over to Bob.
All right, thank you very much for the invitation to speak at this conference. I am honored that you would invite me to that. The title may seem a little bit strange, what quantum measurements measure. On the other hand, I think it is really an important subject in the area of quantum foundations, where we have a bunch of unsolved problems which have been around for many years, and the community is not doing too well in making advances on these problems. As time advances on us, we are thinking of the centenary, depending on how you count that, probably it will come in 2025. But so anyway, this is part of my work on quantum foundations, and let me get started and with a little paradox. This goes back to Einstein in 1927. He said, well, suppose you have a source of a quantum wave. Think of a single particle, but you know a quantum particle is a wave, and it's moving out as a wave and approaching a screen. In those days, you measured things with a fluorescent screen, and suddenly a spot appears at one point on the screen. And this bothered Einstein because this seemed to suggest that this wave was collapsing. And he didn't like things collapsing at speeds greater than that of light. So this is the problem I will be addressing. How are we to understand this? From an experimentalist point of view, and I've actually done somewhat similar experiments myself, the experimentalist will tend to think that the particle is coming out in a straight line from the source up to the screen rather than moving as a wave. So this is, well, maybe the experimentalist has forgotten what he was taught in his first quantum mechanics course, namely that all particles are waves. On the other hand, I can defend the experimentalist in the following sense. You do not have to think of a point particle as moving from the source up to the screen. Instead, you can think of a little wave packet. And wave packets are good quantum mechanical objects, but you see it's again moving almost on a straight line up to the screen. Well, you can say, yeah, well, that's one man's opinion. The experimentalist can then support his opinion in the following way. He puts a collimator between the source and the screen. The collimator is just some heavy piece of metal which will stop the particle, except there is a hole in the collimator, and this lets the particle go through the hole. So most of the time, I mean, the experiment is repeated often, the particle will not get from the source to the screen because it will hit the collimator someplace. But sometimes it will get through. And then you see, if you believe in collapse of the wave function, we have a bit of a problem, because when the particle hits the collimator, metal, the wave function presumably collapses. But on this particular case, you see it's gone through the hole. So what has happened is that the fact that it has not hit the collimator means that the wave packet has been collapsed so that it will fit through the hole. Does that sound sensible? Well, in any case, let me go on. Here I have a second hole in the collimator. But now these two trajectories do not happen simultaneously. Sometimes I get the particle hitting the upper spot, and sometimes the particle hitting the lower spot. But in any case, there's a straight line from the source to where the particle arrives. So from this point of view, one can say that the experimentalist has been justified, and let's stop talking about all of those waves that we learned about in the first course of quantum mechanics. Here I've simply put the last two items at the top of the screen, and now I have a different experiment. Again, I have the two holes in the collimator, but I've taken the fluorescent screen and I moved it very far away. And very far away, it turns out you can have a particle arriving at this point, where, however, there is not a direct straight line between the source and where the particle arrives. How do we understand that? Well, we understand that very well. If you have two openings, you then have interference. And because the wave comes through both openings, it can interfere and the particle or the wave or whatever can show up here. So here we have, in some sense, a very fundamental mystery of quantum mechanics, namely that sometimes it looks as if we should use the particle picture, and sometimes we should use the wave picture. And you can say, well, which of these two is the correct one? Well, you need both of them. But now tell me, which is right? For instance, in this last case, is it the fact that I have a measurement far away that's going to force the wave picture? That seems a little bit odd. Causes usually don't move from future to past. So this is the sort of thing I want to address. So let's move on. And the the way I will say that we can address it is that quantum mechanics allows alternative descriptions of a situation preceding the measurement. One may be preferred to another for understanding what is measured, but the alternative descriptions can be incompatible. That is a very important idea in my explanation of what is going on. So let's move on. Here I have sort of simplified the situation in that I'm using a Mach-Zehnder interferometer rather than two slits, but it's a very similar idea, namely a photon comes, hits a beam splitter, and then it goes either up towards a mirror or down towards a mirror, comes in again. There's interference when it hits a second beam splitter. And as a consequence, the photon, which started off at S1, ends up at detector D1. And this happens every time the experiment is carried out. Well, you say, all right, that's no problem with that. Now let's consider removing the second beam splitter. You see there's no beam splitter here. And now what happens to the particle? Well, sometimes the particle is, the photon, well, it's the same, it is the particle. Sometimes it's detected at D1, and sometimes it's detected at D2. It arrives randomly at one or the other. Let's take the case where it's detected at D2 and ask ourselves, where was it earlier? The experimentalist will usually say, well, it seems plausible that it followed a straight path from the first beam splitter to the mirror and then up to the detector. And we can actually check on that by various means. For instance, we can block the upper path. If we block the upper path, then the particle never is detected by D1, it's always detected by D2. So that suggests the lower path. Or you can put a collimator about the lower path, or you can insert, if you're very clever, something down here which detects which path the particle is going through. And you pretty much convince yourself that indeed we have this situation where with a beam splitter absent, the particle is following the lower, either the lower path or the upper path. But this leads into Wheeler's delayed choice paradox. Wheeler said, well, all right, let's consider the situation, but let's remove or maybe leave in place beam splitter 2 at the very last instant while the particle is still inside the interferometer. Well, you may suppose that that is a rather difficult thing to do because of the short time. Excuse me, my voice goes out frequently, so I'll need a sip of water from time to time. For Wheeler, it wasn't difficult because he knew of this phenomenon, which you probably heard of, by which a galaxy can focus photons coming from a quasar behind it, so they come and then they interfere. The astronomers have seen this. So you imagine this enormous beam splitter, and Wheeler says, well, the paradox is still there. So what shall we do? Well, let's start by taking the following point of view. This whole system here, the second beam splitter, present or absent, plus the two detectors, we can consider as a measuring device. And if the beam splitter is present, then what we are doing is we are measuring the phase difference between the wave on the two paths, right? That determines the interference. So that determines phase. If we remove the beam splitter, on the other hand, then we determine the path. The particle either went through the upper path, C+, or through the lower path, Z- on its way to, say, to D1 or D2. And the use of these symbols suggests a spin half analog, which I find useful in thinking about these things. So Z+ is spin up, Z- is spin down. And what the first beam splitter produces is X+, the coherent combination corresponding to the spin in the plus X direction. So depending on whether the beam splitter is present or absent, this device will measure Sx or it will measure Sz. So now what does quantum mechanics tell us? Well, quantum mechanics tells us we cannot simultaneously measure both path and phase, or if you take the spin a half approach, we cannot simultaneously measure both Sx and Sc. And why not? Well, the first answer might be that, well, those experimenters are not sufficiently clever, and they, with a little bit of thought, they should be able to construct something which will do it. But there's a second answer, which I prefer. The second answer is there is nothing there to be measured. That is, Sx and Sz, the combination, is meaningless. It cannot represent anything that's there. And then even very clever experimenters, including some that have been giving talks at this conference, are not able to measure what isn't there. So let me argue that answer 2 is the right answer in quantum theory, but to discuss why, I need to give you a brief lesson in propositional logic. So here is propositional logic of a simple sort. On this left diagram is the phase space for a good classical particle, position x, momentum p, and the circles indicate regions or properties. That is, if the particle has momentum and position inside the p circle, it has property p. If inside the q circle, it has property q. And if in the intersection between these two circles, it has property P and Q. All right, so that's very simple. And you're familiar with this sort of idea. Well, what about quantum mechanics? Well, quantum mechanics requires Hilbert space. Now, I have to say at this point that my presentation of Hilbert space is just a finite dimensional complex vector space with an inner product. I mean, von Neumann would have turned in his grave to hear such a thing described as a Hilbert space, but allow me the usual interpretation. what does von Neumann tell us? Well, von Neumann tells us that a quantum property, the correspondence of P, is represented by a subspace of the Hilbert space. This is two-dimensional Hilbert space, so a subspace is one-dimensional. I've indicated in this line P. All right, so that represents a property. What about the negation of a property? I didn't say anything about that in the classical case, but the negation of P means all of the points outside the P circle. In the quantum case, however, the negation of P, according to von Neumann, is the subspace which is orthogonal to the original subspace, the projector on that subspace, which is the orthogonal complement of the other projector. And now you see why quantum mechanics is going to give us trouble in terms of logic, because in the classical case, P along with not P cover the entire plane. In the quantum case, there's P and not P lines, but there are lots of things, property I've denoted by Q here, which don't fall on either P or not P, but they're in between. And this gives rise to the question, how are we going to discuss P and Q, that is, in this case, P and Q, in the quantum situation, where these projectors P and Q don't commute. So in the case where the two projectors commute, the product is a projector, and P and Q is just a product projector. So that's fine. The case where PQ is not equal to QP, P and Q do not commute, what should we say? Well, there's standard quantum logic. This is Birkhoff and von Neumann. And they tell you that P and Q is defined as a particular subspace of the Hilbert space, and P or Q is another particular subspace of the Hilbert space. And all problems are solved except for the fact that nobody has yet learned to reason in physical terms using Birkhoff and von Neumann's standard quantum logic. So what I propose is a new quantum logic, the consistent histories. This is the poor man's quantum logic. In this case, if the projectors P and Q do not commute, then P and Q is undefined. It's meaningless. You cannot talk about it. Similarly, P or Q is undefined or meaningless. It's very hard to give a classical analog of the notion of sort of undefined things put together. By talking to my former student Vikesh last night, the following analogy came up. It's only an analogy. So when the cricket teams from India and Pakistan get together, there are certain things which are not discussed. Kashmir, for example. On the other hand, there are things which can be discussed. For example, the miserable effects of the British Raj, which we all agree are a great disaster. So this is just an analogy, but it comes a bit of the way of up to the idea that quantum mechanics allows us situations where we can say one thing about the world, or we can say something else about the world, but trying to put them together, saying they are both true, doesn't work. I call this the single framework rule, and this is a distinctive feature of the consistent histories interpretation of quantum mechanics. So let us now apply this in terms of our previous possibility of removing the second beam splitter. And I'll show you some of the things which consistent histories will say, and maybe some which it can't say, and illustrate. Well, of course, consistent histories on this left side, where you have the beam splitter present, perfectly happy about displaying a wave with coherent phases between the two parts. So in this region, we're talking about a wave. On the other hand, the consistent histories interpretation will also allow you to speak about the particle taking this path or this path, right? That's allowed even though you have the second beam splitter in place. On the other hand, you then arrive at a certain consistency condition, which says if you decided to talk that way, then you are constrained about what you can say quantum mechanically about what happens over here. And the brief result is that what you can say quantum mechanically is that the two detectors end up in an entangled state, a sort of coherent, a Schrodinger cat state, coherent superposition. And now you can see, if you say, well, what are we going to do with, then your question is, what are we going to do with this coherent superposition state? To which I respond, well, that's an element in the big Hilbert space. And so consistent histories allows you to use any such elements, provided you're following the rules. And if you have trouble interpreting that element, well, that's your task. But this is really present. And then moving back a step, since, as you know, there's great difficulty in actually having an experimental measurement, which would determine this nasty Schrodinger cat state, then I can say, well, if you're a practical experimentalist, you probably want to talk about whether detector D1 was triggered or D2 was triggered. That's fine. But in that case, don't talk about which path the particle took, because that's meaningless. Instead, just understand that what you're talking about is the wave. With a beam splitter absent, there's a sort of similar story, but let me not take up time to go through it. The main point is you don't have to say that the future influences the past, as some people have been proposing in quantum foundations. You just have to pay attention to what is meaningful to say. And if your measurement has some sort of outcome, this does affect what is meaningful for you to say about the past. Let's move on. We have now come to this tough topic of unicity. Let me take another sip of water. Unicity is a belief that at any moment of time, the physical world is in a particular state, and anything you can say about it, in terms of physics at least, is either true or false. And my proposal is that in the quantum world, unicity fails. And the quantum counterexample, there are various counterexamples you can make to unicity. I've shown some on the preceding slides, right? You could either talk about the wave preceding that second beam splitter, or the particle on two paths preceding the second beam splitter. And I said both of those are in some sense acceptable quantum descriptions of the world. They're different. You cannot combine them. You cannot say that both are true. Here is maybe a more direct example or counterexample to unicity. So here I have two experimenters. Bob prepares a spin-half particle with Sx equals plus a half and sends it to Alice. Right, and then without it being perturbed on the way, Alice measures not Sx but Sz and finds that Sc is minus a half. All right, so what about the time between those two measurements, after the preparation and before the measurement? What can be said? Well, what Bob says is, look, Sx is equal to plus a half. I, a competent experimenter, prepared it. Alice says Sz equals minus a half. I, a competent experimenter, measured it. And furthermore, I was in Griffith's quantum mechanics course, and he said it was okay. So, which is the right answer here? And the consistent historian said both answers are correct, but you're using two incompatible frameworks which cannot be combined. In quantum mechanics, there may be more than one right answer. Unicity fails. This, by the way, is a notion that many people find extremely objectionable, including David Merman, whose work in quantum foundations is very well known. He just threw up his hands about this and said, look, you cannot have a situation where in one framework something is true, but it isn't true in a different framework. So I sympathize with David's perspective on this. And if you want to join the cubists, go ahead. All I say is there's an alternative which you might want to consider. Well, I'm coming to the end of my talk. So let me end it up with a few words. One of them is relative to the consistent histories approach, which I have been using. There's a challenge. The challenge is find a quantum paradox that I cannot resolve. You know, there are a large number of quantum paradoxes. There is the double slit paradox, and Feynman took a look at it and he said, nobody understands quantum mechanics. And then there is Hardy's paradox, and then there are a whole variety of paradoxes set up by the Tel Aviv group, Aharonov and Weidman, and so on. Then there's the Einstein-Podolsky-Rosen paradox, and then there is the Bell's claim of non-locality because quantum mechanics violates his inequality. I have studied all these things. I have discussed all of these things, not all of them in these chapters, but all of them someplace in the publication. And in all cases, I think I can make sense out of them. Make sense by using Hilbert space quantum mechanics. All properties correspond to subspaces. And then using the sort of logic which I've been indicating, namely, there are sensible ways to combine talk about different things in the Hilbert space and time dependence. And there are restrictions. There are things which don't make sense. And typically what happens in a paradox is that it goes along and it has statement 1 and then statement 2 and statement 3. And I suddenly stop and say, you know, statement 3, you forgot you made statement 1. Yes, but the reply on, well, yeah, but I made statement 1. But I said statement 3 falls in a framework incompatible with statement 1. Your argument fails. You can't put them together. So this is the typical approach. But maybe there are paradoxes which these methods cannot handle. I would be happy to have somebody challenge me with such a paradox, assuming I can understand it. It better be finite dimensional Hilbert space. Okay, plea. The plea is addressed to experts in logical reasoning. Take a look at the new quantum logic. I think it's consistent. I think it hangs together. You cannot derive contradictions using it, but I'm only a lowly physicist. Is there anything wrong with it? And maybe it's already known, although I haven't seen anything in the literature that corresponds to it. It is certainly not the same as standard propositional logic. It is not the same as the quantum logic of Birkhoff and von Neumann, and it's not intuitionistic logic, but then there are many, many other things. Forget the last remark here. So that is the plea. And then the exhortation. So it is the privilege of the old, and I am alas in that stage, to give advice to the young. So my advice is if you're young and looking for a research topic, then I urge you stay away from quantum foundations. Many are wasting their time in this vast swamp and making no progress. Do you really want to join them? Think about that. But then it is the privilege of the young to disregard advice from the old. So if you must get into this mess, start with spin half. That is, start with something simple. Don't start with theorems on quantum field theory. You'll just get lost. If you can't solve the simplest stuff, you won't make progress on the more complicated stuff. And then for spin a half, there's a section 4.6 of my book. But anyway, I think I'm at the half hour. I'm at the half hour limit. So let me stop. Thank you again for your attention, and thank you for the invitation.
Well, thanks, Bob, for a talk in your usual style of being very clear and precise. The house is now open for discussion. If there are questions, people can raise their hand, and I will one by one allow them. Let's see if there are hands raised. I see a lot of young people here, so maybe they have taken your advice number one. Yeah, so let me ask a question, Bob, while other questions may appear. What I see from your talk is that you're advocating following this logic to the next level. I mean, it's the first level at which quantum logic you exposed. So has this been followed to its in a logical way to move on and develop a framework for quantum logic which goes beyond the initial things that you talked about?
No, at least not to my knowledge. But I think if there had been an attempt, I would know about it. Well, the situation, sadly, from my perspective, of course, somebody who develops a theory thinks it's right, and I claim not to be a crackpot. After all, some of this work was done in collaboration with Gell-Mann, who's Nobel laureate, recently died, and with Hartle, who is a cosmologist. The trouble is, it's nobody seems to have really gotten around to taking it seriously. People take a look at it. David Merman has done that and say, well, it's nonsense. Cannot be that way. Others have said it leads into paradoxes. Adrian Kent was one of these people who said, well, it leads into paradoxes, and he published a paper to that effect. And I and Hartle published a response to the paper. So, in that sense, there has been some testing that these rules make sense. On the other hand, there are difficulties which somebody who develops an idea may not spot. There may also be situations of physics where one can say, well, the physical situation seems to make sense, but the rules are not followed. And so this is another attack on this logical structure. But again, I have yet to have encountered such a situation, other than again the paper by Kent that I mentioned.
All right. Thanks, Bob.
Thomas Conrad has a
question.
question. Thomas.
Yes, Conrad has a question. Conrad, please go ahead. I lost connection in between, so.
Yes. Hello, Robert. It's a great honor to listen to you and to be able to ask a question. I just thought of classical logics where you have either A or non-A, and tertium non datur. a third option is not given. And then we know fuzzy logics, right? Fuzzy logics gives values in between, but it's not really, in my opinion, not really something new, because you can always then apply, classical logics to the statements of fuzzy logic. And so what you are saying is that there are kind of, there are statements that cannot be compared, and where the answers are not, where there is not a single answer. So do you think this is kind of, I mean, for me, it seems like this is a very beautiful way of extending classical logics. And what do you think Aristotle would have said to your ideas? Do you think this is the only way that one can extend classical logics, or the simplest way, or something like this?
Well, let's say that I think it is a successful way, but let me say something else about the structure of the extension. There is a rule that forbids combining certain statements. And you can think of that as the rule that corresponds in, if you open a book in logic, the first thing you encounter is there are rules for forming meaningful sentences, right? So every logic and computer scientists are well aware of this. There are rules for writing things. And if you don't follow the rules, you end up with something meaningless, right? If you put Fortran statements into your C program, so much the worse for you. And so the no combining rule, the single framework rule, has a bit of that structure. The trouble, of course, is that instead of having just one language, you're concentrating on one language, say Fortran or C or whatever. You have this whole multiplicity of languages, all of which are possible things. And then if you use a particular one of these languages, the logic is entirely what Aristotle or his followers would have approved of. I mean, you have propositions, you have negations, you have combinations, as long as you stay within this particular language. So that is the structure of it. And it is not at all like a sort of logic which says, well, there is true and then there's false, and then there is something in between, right? So the three-valued logic. Instead, it's saying that there are, this multiplicity of languages. Use any one of them. True and false are what you think of, but you cannot combine them. Do you know anything like that? Does anyone know anything like that?
Yeah, there's one more question by Professor Apurva Patel. Apurva, go ahead.
In consistent histories, you consider all the possibilities which are allowed. So how would you interpret wave function collapse?
Okay, my attitude toward wave function collapse is that it's a means of computation. It's something that can take place in the theorist's notebook, but it has absolutely no counterpart in the laboratory. But let me say a few more words about it. First place, wave function collapse has been interpreted as a sort of a non-local influence. I believe that quantum mechanics has no room for these faster than the speed of light non-local influences. So, and then in the consistent histories approach, rather than collapsing a wave function, there are other things you can do which basically come down to the same thing. One of the other things is while you're applying it, you are always sort of choosing the framework, constructing your logic if you want, if you go along. And so as time progresses, you can add things on to your logical description. And some of these correspond to collapsing the wave function, and some of them don't. So no, it's collapsing the wave function is sort of like addition. You can add things on a piece of paper, but you don't say that corresponds to anything physical going on in the laboratory. Is that okay?
Yeah. All right. Thanks, Bob. I think we have to now close the session. There's one more question by Sarang Bhonsle. I request him to put it in the chat box, which you can read and maybe respond, because we have one more talk in the session. So we'll move on with that. So thanks, Bob, for a very, very interesting talk, and maybe a research program which needs to unfold around it. The
Thanks for
next
inviting.
next speaker in the session is Dr. Brijesh Kumar Agrawala. Dr. Agrawala is an assistant professor in physics department of IISER Pune. He did his PhD from National University of Singapore, and later on did postdoc stints and so on. So he works on condensed matter related problems, uh, non-equilibrium statistical physics, investigations of charge and energy transport in quantum impurity models, universal fluctuation relations, quantum heat engines, and also light matter quantum systems. Today he is going to talk about thermodynamic uncertainty relations in quantum transport theory and experiments. So, Dr. Agrawala, please.
Thanks, Arvind, for this kind introduction. So, can you see my slide? Hello.
Yes, you can.
Oh, you can see my slide, right? Okay.
Yeah, we can see your slides, and we well, now we are seeing some Dropbox folder.
Okay, now it's
this
fine,
is fine.
Right? Okay,
now it's fine.
Perfect. Let me just.
I must say, I mean, unlike most of the speakers in this conference, I'm seeing you for the first time. So welcome.
Thank you. Thanks, Arvind, for the kind introduction once again, and thanks to the organizers for putting up this wonderful conference. So today I'm going to talk about something called as thermodynamic uncertainty relation in the context of quantum transport. And I'll try to give you some of the theoretical results that we obtained in the past 1.5 years, and also we collaborated with some experimentalists, and I'll try to briefly mention some of the experiments as well. So right away, I should thank my collaborators from all around, particularly the experimental group of T.S. Mahesh from IISER Pune and his graduate student Soham, who conducted most of the experiments. Sushant is my PhD student. Onkar is an undergraduate student who did some of these calculations, as well as I collaborate with Divya Segal from University of Toronto, and Oren and Ofi from Weizmann are also perform some experiments to understand this so-called thermodynamic uncertainty relation. So, okay. Yeah, okay. So before I get into the main topic or main theme, let me just briefly tell you what are the things that we are largely interested in. So what we really focus on in the area of open quantum system, and in particular non-equilibrium open quantum system, meaning what we have is essentially a system of interest, which is let's say a quantum, so that can be modeled as certain discrete levels, which can have various type of many body interactions, electron-electron, electron-phonon, and so on and so forth. And this particular system now, you want to, if you want to put it out of equilibrium, there are multiple ways to do it. What you can do is you can bring at least two baths, which could be again fermionic or bosonic, and you put them under different temperature or chemical potential, which can essentially drive current through the system. So that's one way to study non-equilibrium physics. And then, of course, you can ask various type of questions. But just to remind you, these are systems which are not very easy to solve, in a sense that because you have these baths which has infinite degrees of freedom, because these are typically large. You also have, if the system size that you are focusing on, if they are small, there could be a lot of fluctuations. So you really need to understand those as well. There could be something known as non-Markovian effects, which also I'm going to mention very briefly, as well as you could have baths or systems which are having various type of statistics. It could have electrons, it could have phonons, and they obey different statistics. So all this you need to take into account. So then this is in general open quantum system setup, because your system is interacting with the bath and constantly can exchange energy, particle, and so on and so forth. So with this kind of setup, we are interested in various type of understanding various type of physics. In particular, one area that we look at is quantum dynamics, meaning how this system evolves or relaxes to a steady state or equilibrium as a function of time. What this bath does, what happens if you have interactions, so how the relaxation happens. Quantum thermodynamics is another area where if your system size is small, you want to look at how, by taking into account all these quantum effects, how you can build up the notion of thermodynamics even at the small scale. The other thing that I was mentioning, if the system size is small, then you could have the fluctuations which may not be negligible. As we know from equilibrium stat-mech, the relative fluctuations typically goes as 1 over square root of n, where n is the system size. But if the system size is small, the fluctuations could be large. So you may have to go beyond average behavior to see or to understand or to get more information. So in general, the observables may have a probability distribution which need not to look like a Gaussian, look like a Dirac delta kind of distribution. It could be a very different distribution. And in fact, what happens is that for non-equilibrium systems, certain type of these distributions follow universal relations known as fluctuation relations. I'm going to very briefly talk about that as well. And then since you have a multi-terminal kind of setup or multi-bath setup, you have multiple currents flowing through the system. You can as well talk about quantum devices. You can talk about thermoelectric device. You can talk about even diodes. You can start asking questions that how do I realize at this small scale various type of quantum devices, and how I can make them better. Can I make them better using some quantum principles? So these are very general set of questions that we are largely interested in. So with that, let me just give you the plan of in the next 40 minutes or so. I'm going to talk about some of these recently obtained results in the context of thermodynamic uncertainty relation, which from now I'm going to say just TOR. So TOR is essentially the thermodynamic uncertainty relation. So what I'm going to talk about is very briefly introduce the so-called fluctuation relation, and we'll see why that is important in this context. And then I'll introduce what do I mean by this uncertainty relation. And then there are certain experimental studies that we did in collaboration with various groups, in particular something called a steady state TOR and the transient TOR, which is an NMR study which was done in collaboration with my group. So if I have time, I'll go over this experimental part as well, and then I'll summarize my talk. Okay, so first, fluctuation relation. So what is fluctuation relation? So before, in fact, getting into that, let me just very briefly tell you what was known in the, even 20, 25 years back, what was known in the non-equilibrium context in the certain universal relations that were known only in the linear response regime. So by linear response, what I mean is that your system is very close to equilibrium. Okay, so and this linear response regime has been summarized by universal relations which are known, for example, Onsager reciprocity relation or fluctuation dissipation relation. To give you one simple example, once again, let's just think of a quantum system, which, or it could be even classical, but let's say it's quantum system, which is in contact with two electronic reservoirs, and they are at different chemical potential. So then you know that by second law, my current will flow from higher chemical potential to lower chemical potential. So then if the system is, let's say, in a steady state, then a constant current is flowing, which is the average J, and the current you can expand in this manner. So the current is certainly a function of the bias, the voltage. So V is mu L minus mu R, which is the bias difference. So you can certainly expand your current in this following manner. Okay, but you can go ahead and look at what about the second moment or second cumulant of the current. So this is the second cumulant or the fluctuation, right? So you can, so this double angular bracket, I mean, is a fluctuation. So the fluctuation also you can expand in the same manner, but note that the fluctuation or the noise does not vanishes in equilibrium, unlike current, which vanishes in equilibrium, right? But the noise will certainly have an equilibrium component, and then it could have those non-equilibrium components because you turn on your bias. So what people knew in 50s, since 50s, is that at least in this linear response, meaning if your bias is small, then in the linear response, this S0 connects to G1 in a universal manner. And that is something known as Johnson-Nyquist theorem, that conductance, so G1 is nothing but the conductance. That's like the Ohm's law, right? Conductance is proportional to the current noise at equilibrium, because this S0 is equilibrium noise. And this is universal. This is independent of whether you have a classical or a quantum system, right? So, but this is, the restriction is that this is in linear response. So the question that haunted physicists for a very long time was, what happens beyond linear response? Do we receive this kind of universal relations even beyond a linear response? And the answer turned out to be yes. There exist universal relations even beyond linear response. And in fact, they were formulated in the by the name, the so-called fluctuation relation. Now, what fluctuation relation is, there are many versions of it, but let me very briefly mention one version in this context of charge transport, where you have this current that is flowing, and let's say you are looking at, in a certain time window, how many electrons, let's say, have flown from left to the right. Now that's a stochastic quantity, right? Because ultimately there are uncertainties, there are fluctuations which are happening because underlying quantum principle as well as because of thermal fluctuations. So there are various fluctuations which makes these quantities random, and therefore you can talk about distribution. So what fluctuation relations tells you is that the probability of electron, number of electron in a certain time window going from high bias to low bias, okay, is exponentially larger. Look at this V. V is the bias, and T is the temperature, is exponentially larger than electron flowing in the opposite direction. So once again, electron in a certain window, number of electrons in a certain time window flowing from high bias to low bias is exponentially larger than the opposite flow. So, so this is a probabilistic statement. This is not violating second law. Second law that we know is at the level of ensemble average. So if you do that, certainly you will get the second law. But at the level of probabilistic distribution, there is an opposite flow that can happen, which is an instantaneous kind of a thing. So this is valid for any away from linear response. This is valid for, in general, for any bias. So this is quite universal. It requires certain conditions. I'm not getting into that. But if you preserve some of these conditions, this relation is going to be valid. So if it is valid in throughout the regime, you can certainly show that if you take the close to equilibrium or linear response regime, you get back whatever you knew in 1950s, all those fluctuation dissipation or Johnson-Nyquist theorem, all that you get back. But what more? What do you get more? You get the following thing. So if you now recall those relations that I wrote down for current and fluctuation, or the second cumulant. Similarly, I can write down third and fourth cumulant, and I can carry on. I can carry on doing that, and I can expand in this kind of series as a function of bias. Now, as a consequence of this fluctuation symmetry, what you can actually show, so initially we knew only this, that S0 is related to G1, which is linear response. Now, because of this relation, what you can show is that you get, in fact, infinite number of relations between involving these transport coefficients. So in fact, what happens is not only this is true, but S1 connects to G2, R1 connects to T0, and so on and so forth. You have many such relations, in fact, infinite number of such relations, just an outcome of this simple relation. Okay, so that's a fluctuation symmetry. That's an outcome of the fluctuation symmetry. So it gives you relation between nonlinear coefficients. So for if you're interested in knowing more about this, there are very interesting review articles written here, which you can look at. Now let me get into the thermodynamic uncertainty relation. So what is this relation? So this relation is essentially a bound, and it talks about it's essentially called a cost precision trade-off bound or trade-off relation. So imagine you have just a simple two-terminal situation. Two-terminal means you have a system which is connected to two bars, and you have a single affinity. That means you have just a difference of bias, let's say. So you have a single current. You don't have multiple currents. So you just have a single current which is governed by a single affinity. So then if the underlying process is a Markovian, now I guess many of you are aware of what Markovian process is. So that's essentially that if you write down the equation of motion for the system state, they essentially governed by Pauli type rate equations. So if you have something like that, then this particular bound, which was given first by Seifert, which was numerically conjectured, is the following. You look at the current. So the current is in the steady state. So you look at this fluctuation over the current square. This is like the relative uncertainty. Okay. Now this is something which is also, you can say, precision. You want this guy to be as small as you can. That means your noise will be small and current will be large, and so the relative fluctuation will be small. So this is like a precision that you want. So how precise you can make? It turns out that you cannot make such a quantity arbitrarily precise, but it's essentially bounded by a so-called entropy production. So entropy production is what? When you're driving system away from equilibrium, you're essentially generating entropy, you're producing entropy, which is given by nothing but current that is flowing through the system times the affinity. So if you're sitting in equilibrium, you're not producing entropy. So essentially, any of this kind of precision, any observable, in fact, this goes beyond such a relation. I mean, which is where I'm just looking at the current, but apparently it turns out that you look at any type of correlation and its fluctuation. If your system is following Markov process, is always getting bounded by the entropy production. So that is the main theorem. Here I'm showing it for the current only. So for two terminal setup, the entropy production, you can simply, since you have only one affinity, which is V over T, where V is the bias, and the current is just a simple J average, that's your entropy production. So now there is a greater than equal to sign. So there is a lower bound, which is 2. So when does the equality happen? So equality happens simply in the linear response. So if you take the limit that the bias is small, the V tends to 0, then you actually, what this relation gives you is precisely Johnson-Nyquist kind of relation. But now what it says that if you go beyond linear response, you hit an inequality sign. All right. So this relation was given for Markov process for non-equilibrium system. So the question that we started asking was that how universal this relation is. Does it even hold beyond Markovian? Can we check that? And if it is universal, then can I prove it? Can I try to prove it from the fluctuation symmetry? Because as I mentioned, the fluctuation relation or fluctuation symmetry is universal. So and an outcome of fluctuation symmetry is that, for example, you recover everything as you know from second law of thermodynamics. For example, if you think of an engine, efficiency gets bounded by the Carnot value. So all that is an outcome of fluctuation symmetry. So the idea was that can I sort of get, if this bound is universal, let's say, can I prove it from fluctuation symmetry? And are there any quantum effects, since we are interested in quantum system? So this was the first question that we started asking in this direction, and this was a paper, the first paper in this field. And then there were a lot of, so the first paper was given by Udo Seifert, which very conjectured, and then over the year now, there are many papers that have been written in this line. But let me now tell you what we did. So once again, what we have is the current, the second cumulant, the third cumulant, and you have this series expansion, right? Now, I said that I want to use the fluctuation symmetry. Now, how do you use fluctuation symmetry? You know, because of fluctuation symmetry, you have these universal relations between these transport coefficients, right? This is where I'm using the fluctuation symmetry. So now, what you have as a if you remember the TUR, the tour, the left-hand side is this, right? You want to show whether it's greater, you want to check whether it's greater than 2 or not. Under what condition this is always greater than 2. So note that this sigma average is, as I mentioned, is just current times affinity. So if you substitute that, this J cancels this J average, one J gets cancelled, and you finally get this guy, right? I simply get this guy because one of the J is getting cancelled, just which is coming from entropy production. So you know the series expansion for J, you know series expansion for this guy as well, which are these. If you take that and if you do perturbative expansion, you do sort of collect order by order term in bias, you first recover the result 2, which essentially, as you can see, if you take the bias tends to 0, you recover, that's a linear response. But then the next term that you get, the first contribution that you get is a V square. You don't get any term which is V. And that comes from the fact that there is a time reversal symmetry underlying. Because if you get a V dependent term, you can very simply violate this to that order, because making V to minus V is very simple. You just change the direction of your bias. But so that is what is happening. So you get something which is this, okay, as a first correction. And then what is this other coefficient? So there is a G1. Now G1 is a conductance, which is always positive, right? And then you get something which is R1. Now what is R1? R1 is the third cumulant for linear coefficient. Now right away I should tell that we know overall, for example, noise is always positive. Overall this is positive, but it doesn't tell you anything that whether S1, S2, S3 will be positive or not. Similarly here for third cumulant, you don't know whether R1 will be positive or not. If there is, it's not guaranteed. Okay. So so it turns out that this can in fact change sign. So the point is that if it changes sign, if it is negative, if it becomes negative, then at least to this order, this bound can go below 2, right? So how this R1 is given? So this R1 you can as well write in terms of the other coefficients because there are these relations, but note that the R1 is simply just the first term of the third cumulant. So this can change sign. That is what I'm going to show you. And note that this simple calculation, this is valid for both classical and quantum system because all I have used is fluctuation relation, which is independent of sort of whether you're treating the system classically or quantum mechanically. Now, since you need to know in order to check anything about R1, you need to know the current and fluctuation. So now getting that for any type of interacting system is non-trivial. So what you can do, we as a theoretical physicist always like non-interacting systems because you can always compute everything exactly. So if you have such a system where let's say you have a kind of tight binding chain coupled to two bars, and there are no nonlinear interaction or many body interaction, it's simply quadratic kind of system, you can compute current and fluctuation exactly, and the current is given by Large-Focal very famous Landauer formula, where you see that there is a Fermi function which are coming from these paths, from the left path and the right path. These are Fermi function, and this T is what we call transmission function, which essentially captures that with what probability electron flows from left to right. Okay, this is basically the transmission probability that given a mode or given electron certain energy, with what probability it crosses the junction. Now that is very crucial. And similarly, you can write down the fluctuation, which is again given in terms of these Fermi functions and the transmission, but that's not it. It also given in terms of transmission square. Now that's also very important. Okay, and you see a crucial negative sign here. Okay, so now what you want, you are looking for this quantity called R1, which you can very simply obtain by looking at all these transport coefficients, and this R1 is simply given by this. Just you don't have to really pay attention to all these terms, but look at this particular term, which is 1 minus 6. And so transmission, Fermi function, these are all positive. Now if there was a plus sign, things would have been different. It would be always positive, but because of this presence of minus sign, what could happen is that there is a chance that R1 could be negative, and that's where you can start seeing that the bound can go below 2. Okay, so essentially, if you want this guy to be negative to see any signature of violation, all you need to play with is the structure of the transmission, because you're finally doing an integration. So your structure of the transmission, and you can probably think of changing the temperatures and chemical potential because you have the Fermi function also sitting here. So if you manipulate that, you probably can still get a violation. But before getting into that, what we checked is that if the transmission through the junction is very small, then you can always show that the tour is valid. Okay, so this is, so I'm now going to show certain limiting cases. So one limit is that if the transmission is very small, which is often indicated as a Poisson process, the tour is always greater than 2. We also are able to show that if the transmission is constant. Now the transmission is something that depends on your junction structure. So there could be many possibilities. So if you have very small transmission, it's valid. If you have constant transmission, it's valid. But then there is an interesting limit which we found, which is the following. It's something called a resonant tunneling condition. Now, what is that? Resonant tunneling condition is essentially a condition where your system that is talking to the bath, if that coupling is very weak, then just from the picture of density of state, these are typically kind of very sharp functions. So your transmission is kind of very sharp about certain energy of the system. So if that is the case, and if your Fermi functions are kind of broad, that means your temperature is quite relatively large. So you are in this regime. So if your Fermi functions are broad and your transmission is sharp, then you can very simply do some manipulation to this R1. And if you now invoke the fact that you demand R1 to be less than 0, because that's where you are interested, you want to see if there is any violation, that gives you some interesting condition, which is this, that this tau2 by tau1 is greater than 2/3. If that happens, you will hit a violation. Now, what is tau2 by tau1? They are nothing but integration of transmission for tau1, and tau2 is integration of transmission square. So note that where is transmission square coming? Because you have transmission square sitting in the fluctuation. So if you have this, then you will start getting violation. Now let us see some example. So here we cooked up certain, as I said, this is very general. The current and fluctuation expressions are very general. You can have arbitrary junction as long as the system is non-interacting. So we took very simple examples, and here let me just focus on a simple single quantum dot coupled to two baths and a double quantum dot coupled to two baths. So in both these, the reason of choosing these two is that because the transmission looks very, very different. So in the single dot, if you look at the transmission in the weak coupling, weak system path coupling, which is gamma, it's simply a Lorentzian. Okay. Whereas for double dot, you get essentially, because you have two resonant frequencies, you get two peaks in the weak coupling. But if you make the coupling very, very strong, this single dot case, it just gets more and more flat, because remember, the broadening is proportional to the system path coupling. So it becomes very broad and kind of constant, which is this plot. And if you make for the double dot coupling to be very strong, then essentially what is happening is that the transmission will become very small, because your omega becomes much smaller compared to gamma. So it's like each dot is equilibrating with its own path, and the transport is not happening. So transmission becomes very small. So you can play with this transmission by tuning all these parameters. And now your hope is to see if there is any violation. Now, here is what the first plot, which is essentially for the single dot, the transmission is Lorentzian. And now you see, as a function of gamma, where gamma is the system path coupling, if gamma is quite large, you see this R1 going negative, and that's the violation regime. Okay, the violation is not significant, but still it's going negative. So, but you don't get the violation in the weak coupling, at least for single dot. The reason is actually very simple, because for a single dot in weak coupling, you can actually write down a master equation, a quantum master equation, which looks like very much like a Pauli master equation, which is Markovian. And that's why the bound is always going to be greater than 2, meaning R1 is positive. But if you have coupling to be strong, then you cannot have a rate type equation, a Pauli type rate equation, and that's where you can start seeing the violation. So this is, you can also show analytically, which we have done in the paper. I'm not going to show that, but here the violation is at the strong coupling. Now, what happens for double dot? Well, for double dot, it's actually the opposite regime. You have a certain intermediate gamma regime where you see the violation, all right? And in fact, that exactly corroborates with the fact that exactly in that where you see the violation, the tau2 by tau1 is precisely greater than 2/3, which we demanded. So here, we still don't understand why this violation happened, but a very naive point to mention is that your gamma is of the order of omega. If you look at this, your gamma violation of the gamma is of the order of omega. Now, what happens here is that in this kind of quantum systems, if you write down the density matrix for this double quantum dot, you could have population getting coupled to coherences. And that's the region where you cannot demand only Pauli type rate equation for population. And that's one of the way to see that violation is happening. So essentially, by playing with transmission and tuning the parameters, you can understand in what regime you could expect the violation. Okay, so this is sort of the summary of this part, that indeed this R1 can change sign, and you see if your system kind of goes beyond Markovian, there is no reason it may not be valid. And this is coming just from the fact of fluctuation symmetry, which is quite universal. So we have tried to give out certain reasons of why that you're under certain regime, the system can go beyond Markovian limit, and you can start seeing these violations. So, so this was the context of charge transport, but nothing surprising happens even for energy transport or heat transport. You can as well extend this whole analysis. So far, we have done only the chemical potential difference, but let's say you don't do that, but you make the temperature difference. What would happen? So essentially, you can do the same algebra, you get similar type of thing. There is no surprise. And if you now look at the thermal current that electrons are carrying, if you do that, you once again get a very similar kind of physics. You see the violation, the R1 goes negative, and you once again get a condition which is tau2 by tau1 greater than 2/3. But note that this tau2 by tau1 now is slightly different. It's not exactly like before, because since now you're looking at the thermal current, you have this factor epsilon minus mu. Remember, in the charge current case, you don't have this factor. But now, because you're looking at energy current or thermal current to be precise, or heat current, you have this epsilon minus mu. So you have to take care of that factor here, and then again you can formulate your entire thing. So there is indeed a violation even for thermal current for where the carriers are electron. And if you numerically check what a broad parameter regime, there is a basing where you can see quite a bit of a violation. But we actually went beyond this and started asking the question that when heat current is flowing, the carriers could be different. It could be by electrons, it could be by phonons, where think of you have collections of harmonic oscillators which are connected to two bars. and the phonons are carrying heat. So basically the question that we started asking, that how does the two depends on the statistics of the carriers. Okay. So interestingly, what we found is that if I have a system where it's just collections of harmonic oscillator coupled to the bath, you can show that there is no violation. No matter what regime, Markovian, non-Markovian is always going to be valid. But then we actually wanted to go beyond that, and we started looking at, okay, what about other kind of statistics? So this is governed by bosonic statistics. As you see here, this n are Bose functions. Okay, you do have transmission, but note there is a plus sign. Earlier, when you did Fermi problem, we had the minus sign, and that's why you started. So this plus minus should remind you the sign difference between Bose and Fermi function. That's essentially what is happening here. But then you could think of some kind of a hybrid problem, which is like a single spin coupled to two bath. That's a famous non-equilibrium spin boson model. So your spin could be like a two level, which is essentially can give you Fermi-like function, right? Whereas the baths will give you Bose-like function. So you essentially have a very mixed kind of a statistics. And what we found is that again, I get a minus sign, but now there is a Bose function sitting coming from the bath. Whereas the previous example that I showed for electron, where heat current is flowing, you see all as Fermi functions, because this is purely electron, this is purely boson, but this is kind of a mixed electron and kind of Fermi-like and Bose-like function, and that's why you get a minus sign. So apparently in both these cases, because of the presence of minus signs, you start seeing violation, which giving us some indication about the size of the Hilbert space, because for the harmonic oscillator is kind of infinite, whereas these are finite size Hilbert spaces, and maybe that's the reason that you start seeing violation here, but not in the phonon case, which you can show very rigorously that is always valid. So here is the spin boson, where if you play again with the transmission, you can see that R1 goes below 2. So there is a regime where you can see the violation. Okay, so up to this, what I showed is that things can go below 2, but I didn't really answer that how below it can go. Okay, so we didn't tackle that. We although we ran a lot of numerical simulations, and we found something around 1.2, 1.24 was kind of the answer that we got for electron transport at least. And then a paper came out which took some geometrical sort of an approach to prove that under certain limit, the bound need not to be 2. It's quite a general proof. It can be 1. So far, whatever I showed satisfies this result, which came out last year. So our bound was always, our bound can go below 2, but certainly it was always above 1. Now the outcome of such kind of bound actually is overwhelming. I mean, there are many interesting results that one can actually generalize just from this bound. And one of the bound that Udo Seifert once again extended for multi-current system, where you can talk about efficiency. And this is one very interesting bound. And if you have time, please take a look at this paper where they extended this whole analysis of tool in the context of bounding the efficiency of an engine. Which, if you know earlier, that is efficiency of an engine is just bounded by Carnot, but now because this relation involves first and the second, or the fluctuation, the bound is now more tight, and it's given in terms of the fluctuations. So you see, for small system, this could be very, very important, because you're now taking into account fluctuations, and that helps you to bound even further. Okay, so this is actually quite interesting in that sense. Okay, so I'm now, since I have another 14 minutes or so, I'm just going to very briefly flash some of our experimental results. So the first one is the steady state. So far, what I mentioned is the tool in the steady state. If you remember the currents, I expanded about the bias or the temperature difference, which are, of course, the current is calculated in the steady state. Remember the Landauer formula. So in the steady state, we went ahead. So there was group by Oren and Ophir. So Oren Tao's group in Israel, in Weizmann. So they could actually measure both current and noise in atomic scale junction. Okay, so they had the data. So what we did was to proceed with their data and try to analyze what happens to the two, because that's all we need. We need the current and the fluctuation. So these are some plots of transmission. I'm not going to again spend time here. I would rather going to talk about the NMR study that we did. So here, all I wanted to mention is that with the obtained data, we could actually, which is basically the current and noise. So from here, if we know that, we can actually put this and try to look at what we get for the tool. And here is just one final sort of just only plot that I want to show, is that for this experimental setup, what we found is that the tour is always getting satisfied. So we didn't find a regime where there is a violation. And one reason is that the violation regime actually is not a big regime. I mean, it's a very you need certain parameters in proper regime to see the violation. So unfortunately, their experimental data that they had was not in the regime where we start seeing the violation. So in fact, they had a constant transmission kind of a picture where I already showed you that the tour is going to be valid. But in any case, this at least shows that under certain limit this is valid. So this paper was to at least try to test or assess the validity of the uncertainty bound. Okay, so now in another 10 minutes or so, let me tell you about the other situation. So far we looked at this bound in the steady state. But now in recent time, people have also tried to extend that for the transient case. Now, what do I mean by transient? Well, in the transient case, you cannot talk about rates. So far, when I was talking about entropy production, it's actually entropy production rate, right? But now, because you are in the transient, you have to really talk about the integrated quantity by itself. Things doesn't scale with time anymore, right? So a simplest situation that I can tell you is the following for the transient. So imagine you have two systems, two independent systems, which are initially at some temperature T1 and T2. Okay, and they are in their own canonical distribution, and then what you do is you just couple these two systems. So because of the coupling, now current will start to flow, and you can start asking the question that let me look at in a certain time window how much current or what is the amount of heat that is. So Q average is the amount of heat that is flowing from one system to the other. So then very similar like tour in the steady state, I construct this quantity, which is the noise over, so this is like the relative uncertainty, and this is now capital sigma, which essentially should remind us that this is not the rate but an integrated quantity. Okay, so I'll just give you an example, and the question is that whether this is even in the transient, whether this is valid or not given this kind of a bipartite setup. So we first we actually did an experimental work in collaboration with Mahesh group. So the first task is to how do you measure this, guys? How do you get this Q and Q square in experiment? It's actually very simple, and which was proved by BBY in 2018, which is that if you do quantum state tomography and get the state of this whole system, okay, at any instant of time t, then you can actually get all the moments of heat at that time. So this is a wonderful result where you see this rho is the entire system's density matrix, and rho 0 is the initial preparation that that's in your hand, and then rho tau is evolving under unitary. So these are the set of conditions under which this was derived. The initial condition is decoupled, and each are sitting in equilibrium with respect to canonical. The evolution is happening under certain unitary evolution. The global this is a global evolution. So this is what you want to measure in your, so tomography will give you this, quantum state tomography will give you this, and the another assumption is that certainly the energy is changing, but you spend some amount of work in coupling these two systems. So certainly you have to now identify what is heat, what is work. So if you assume that this this turning on the coupling, you didn't spend much of the energy, then you can which is called the weak coupling. The weak coupling limit, you can sort of argue that the change of energy you can interpret as heat. So under this set of limit, they have proved this, and then what happens is that entropy production, as I mentioned it again, current times affinity, or in this case it's not the rate because it's the total entropy production is current times the heat. The current times the affinity, and affinity is just delta beta, which is the inverse temperature difference. So given that, then once again this tour essentially becomes this, right? Because you sigma is again just like before, sigma is now delta beta q, and that cancels one of the q, and you get this. And the question is, what happens to this guy? And just to flash one of the other work that in this direction, what we did in collaboration with Mahesh and Shrom, their group is essentially that there is a fluctuation relation once again in the transient case as well for this probability distribution of heat. And this fluctuation relation is what we also experimentally we verified. So if you're interested, please look at it. But again, coming back to this particular tool case, so what we essentially realized is this particular Hamiltonian. So this is like, so we have essentially two qubits, which is H1 and H2, let's say, and then this is the coupling between these two qubits. Okay, and experimentally, what you do is to actually have prepare this one at some temperature, let's say T1, and this one at some temperature T2. So this is qubit 1 and qubit 2. So they are at different temperature, and then you have this coupling which allow heat exchange. Now, important feature here is that what we used as a coupling is that this coupling commutes with the total Hamiltonian. Now, that's something called as known as a thermal coupling, and that essentially makes sure whatever energy change that happens exact in one of the system exactly gets deposited in the other. So there is no work done in turning on the coupling. So that's actually good, because then you are not in a position where you have to understand what is weak coupling and so on and so forth. So this is this is a thermal coupling. So that's experimentally realized. So this is a pulse scheme, which I'm not going to mention. This is the internal molecular Hamiltonian, which essentially you have for this molecule. And then you essentially apply this pulse scheme to realize this Hamiltonian. And then you can do your quantum state tomography. And this is one result which essentially shows that there is very nice agreement between theory and experiment. This is the agreement of the initial state preparation, which is a canonical, as I said, is a direct product between the two systems. And this is the corresponding experimental result with the fidelity, which is around more than 0.98. So which is very good. So this is the, so with this, knowing just these states, now if you plug in those expressions that I showed you, then you basically get all the moments in principle. But for Tour, you need only the first and the second cumulant, right? And then just a couple of, this one slide with some results from the paper. What we apparently see is that there is again a certain regime where you don't see any violation. Okay, and because you see this delta beta, this -2. So this is positive. This is always positive. That means there is no violation. Whereas you can find some other regime and in a way you can start to see some violation. And you see, look at the blue plot. This blue plot is where you see there is negative. And again, just like the steady state, once again here as well, you see the third cumulant also becoming negative, precisely when you have the violation. So which again connects to our steady state observation, which was that R1, remember the R1 was the third cumulant coefficient, and that was negative. And here also we see even for the transient rate that happens. And also what we observe is that the J is what? J is the coupling between the two systems. Beta is the inverse temperature, nu0 is the frequency of the qubit. So if J is small, okay, relative to the frequency, so that means that's what the weak coupling, we always see that this is true, there is no violation. Whereas if the J is large or J tau is large, you start to see violation. And that we also understand very simply from very simple analytical results which we recently put up. And this analytical result is essentially that for this spin system, again 2 qubit, the same system, if you analyze, you very nicely see that there is a contribution which is just a thermal, okay, which is this term. And then you have exactly the entropy production, but as a negative contribution. Okay, now entropy production is always positive. Average entropy production is just the second law, that's always positive. So if there was a plus sign, you win the case. I mean, your TUR is always greater than 2, but there is a negative sign, and that indicates that you could have a violation, because if you didn't have the second term, this term is always greater than 2. Always, yeah. This is, you can prove that this is all x cot hyperbolic x is always greater than 1. So if you have this, you would have 1. But there is this entropy production which comes as a negative sign. And now if you demand that you want to go below 2, it gives you a condition which is that it gives you a condition on the coupling which has to be greater than 2/3. That's again kind of very much like a steady state kind of a condition that we are getting here. And that's precisely this is the regime where you start to see the violation. Okay. This is the regime. This blue regime is where you see the violation. And that exactly matches with what we observed also experimentally. Now, just to end the talk, you can think of, okay, this is again like a 2-qubit, which is like following kind of a Fermi-like statistics. What happens if I change this and make, instead of 2-qubit, just 2 oscillator, 2 harmonic oscillator, different temperature, and they're coupled. Okay, if you do that, if you do this calculation, which is this 2 coupled oscillator and coupled by this, again thermal coupling limit, what you can show is, it's a very simple calculation. You again get this universal kind of a term, which is always greater than 2, but now there is a plus sign. Now there is a plus sign with the entropy production. So you always win. You always greater than 2, which is like again steady state. If you remember, for an oscillator system, it was always greater than 2. But the moment you going beyond that, your Hilbert space is kind of finite. You start seeing this kind of negative and violation. So with that, I want to stop. Okay, not stop, but I want to just summarize. But before that, let me just mention once again, for the transient case, since I can go below 2, you can ask what is the minimal bound, what is the lowest bound that is possible. So that also was recently answered from the fluctuation symmetry. And if someone is interested, please look at this 2 set of paper where they very nicely showed the lowest bound possible. And of course, our experiment, something that I didn't show you, but experimentally also we checked that we always are above these bounds. So we certainly we follow these bounds. So with that, let me just summarize the talk. So fluctuation symmetry is a very important relation in the context of non-equilibrium physics. It's something it's very universal. It tells you something. In terms of this response coefficients that I mentioned are very, very crucial. One message is certainly, if you're looking at small systems, they require statistical description. There are important information that you can get by studying the fluctuations. And now this is the tool is one of the bound that involves the fluctuation, which is very nice. And there are interesting outcomes of this bound, which I flashed this Udo's paper, where they now bound the efficiency not only in terms of the Carnot, but there are fluctuations sitting in that bound, which is very nice. Now, Tour, as I mentioned, the traditional bound that was given initially for Markovian system, it's not universal. There are possibilities that you can have violations in that, which can depend certainly on the nature of the transmission, which as well as the statistics of particles. And I also showed you some of the experimental results that we obtained in 2 regimes, in steady state atomic junctions and in the transient case for the NMR setup. So with that, I want to thank all of you for your attention. And I want to once again thanks Mahesh's group and Soham, who is the graduate student, for doing the NMR experiment, Orange group for doing the atomic conductor experiments. And these are, Divira and Onkar is an undergraduate student. Divira is from Toronto, and Shushant is my PhD student who did most of these calculations. So with that, I want to stop here and would love to take questions if there are any.
Well, thank you for a very detailed talk. The house is now open for questions. Let me see if there are any hands raised. Usha Devi has a question. Usha, please go ahead.
Okay. Thank you for the detailed talk. I would like to know if there is any kind of classical limit to this thermodynamic uncertainty relation, because what you talked to about is on quantum systems essentially.
Right.
But
right.
There would be a classical limit. What would it imply in classical limit, and what would happen to the bound and all that kind of a
okay.
situation?
So in fact, this bound, if you look at the first work where this bound came, it was actually very much for a classical system, where, as I mentioned, that's true for Markov process. So there is this relation. If you just look at by itself, there is no quantum information already. I mean, this is just simply current, its fluctuation and entropy production, which is always there if you have current. So this bound by itself is valid even for classical system. I mean, you don't have to take any limit. So, but what we were interested was to look at quantum system But certainly you can explore this for classical system, where if you want to see violation, maybe you should look at the non-Markovian regime. So you can, yeah, and probably that also can
But
give
there is
you.
no fermionic and bosonic kind
Oh,
of
that's true. Yes.
analogies.
Right. That's not there. That's right. But certainly, for example, in the steady state, the bosonic case that I showed, the heat transport, the first one, this one, for example. So here the classical limit exists, right? Because the Bose function,
Okay.
and you can
Yeah.
again show that this is still valid. So this
Right.
relation by itself is valid even for classical domain. But the main point is that if you satisfy the Markovian property, then this is always going to be greater than 2, which was shown, which is now shown by also very detailed proof by Gingrich from MIT. But to see or to understand whether what happens beyond that, you can even take a classical example and look at, for example, any kind of non-Markovian dynamics.
Okay.
Right.
Thank you.
Thanks.
Well, I don't see any other question. Is there any other question? If there is none, which I see there's no hands raised, I once again thank the speaker, and I would also like to thank both the speakers in the session. There's a late session by Indian standard. It's 9 p.m. I still see people attending it. Thanks to Bob Griffiths and to Dr. Agrawala
Thank you,
for
Arvind.
delivering these talks. Thank you very much.
Thank you, Arvind.
We would now close the session. Organizers may have any announcements to make, maybe not. So we close this session and thank the speakers.